So this is the second of 2 lectures on the Rsa Cryptosystem. So let's just review a little bit. There is always Fermat's little theorem, which says if you take a prime number p and an integer a, where the GCD, the greatest common divisor of a and p, is 1, then a to the power p minus 1 is always congruent to 1 mod p. But this congruence works for a modulus that's a prime, but not for a composite modulus. And there is Theorem 3.1, which is a special case of Euler's generalization of Fermat's theorem. So this is called Euler's formula for PQ. So in this case, P and Q are 2 different primes. These are distinct primes. And what Euler's formula says is that if the GCD, the greatest common divisor of A and PQ, is 1, so that means A is divisible neither by P or by Q, then the simplest form is that A to the P minus 1, Q minus 1 is congruent to 1 mod PQ. And somewhat more generally, if we let G be the greatest common divisor of P minus 1 and Q minus 1, so G divides both of these numbers, we can actually make this exponent a little bit smaller. A to the P minus 1, Q minus 1 divided by G is congruent to 1 mod PQ. So for example, if we have, let's say, P equals 7 and Q equals 13, or let's just say let P equals 7 and Q equals 13, if A is relatively prime, see, what is PQ? So then PQ is 7 times 13 is 91. So if A is relatively prime to 91, then A to the power, let's see, what is P minus 1, Q minus 1? P minus 1, Q minus 1 is 6 times 12 is 72. So A to the 72nd power is congruent to 1 mod 91. But in fact, if we let G be the greatest common divisor of P minus 1 and Q minus 1, so this is the greatest common divisor of 6 and 12, which is 6. So in that case, if A and 91 are relatively prime, then A to the power P minus 1, Q minus 1 divided by 6, 72 over 6, or A to the 12th is congruent to 1 mod 91. So if you take a number A and you want to find the smallest power of A, which is congruent to 1 mod 91, this says that A to the 72nd definitely works, but this says, in fact, that a smaller power, much smaller, A to the 12th, also works. So the Rsa Cryptosystem is based on the problem of what one might say, taking square roots or cube roots or higher roots of numbers mod p, and proposition 3.2 is the simplest case of this. So p is a prime number, e is a positive integer, and we want e to be relatively prime to p minus 1. And we want to solve the congruence x to the e congruent to c mod p. So I should say, given this number c, find a number x such that x to the e power is c mod p. So this is almost like saying x is like the eth root of c, right? I mean, this doesn't really mean anything, but this is how you would understand this if these were real numbers. You want to find a number whose eth power is c, so x is like the eth root of c. And the solution comes as follows: because the GCD of e and p minus 1 is 1, then there exists an integer d such that DE is congruent to 1 mod p. This is just solving this linear congruence using the Euclidean algorithm. And the solution of this congruence is that x be congruent to c to the power d mod p. That's the solution of this congruence. Why? Because if you take x to the e, that's c to the d to the e, that's c to the de, de is 1 plus de is congruent to 1. Sorry. E is relatively prime to p minus 1. So that means there exists a d such that d times e is congruent to 1 modulo p minus 1. So de is 1 plus some multiple of p minus 1. That's c times c to the p minus 1 to the k, just using the rules of exponents. But c, if c is not relatively prime to p, this is just 0. It's a 0. C is relatively prime to p, this is 1. C to the p minus 1 is 1, so this is just c mod p. So this is what we discussed in the previous lecture. Now, what we want to do is consider, so this is easy. So it's easy to solve x to the e congruent to c mod p. I claim that it is hard, I'll put this in quotation marks, hard, it depends on what you know. It's hard, or certainly it's harder, to solve an equation of the form x to the e congruent to c mod a modulus, which is a product of 2 primes. And the Rsa Cryptosystem is based on the difficulty of solving this congruence. Now, if you know this modulus is p times q, it's not hard to solve the congruence. There's a way to do that. So this is proposition 3.5. So we have p and q distinct primes. We have a number e, an exponent, which is a positive integer. And the greatest common divisor of e with p minus 1 times q minus 1 is 1. And given c, find, or that means compute, the exponent e that's such that you can given c, find x such that x to the e is congruent to c mod pq. So you want to find the eth root of c. And there's a method to do this, right? So, solution. Because the GCD of E and P minus 1 times Q minus 1 is 1, there exists, and you can compute, a number D, positive integer, let's say, such that DE is congruent to 1 mod P minus 1 Q minus 1. So if you know this modulus is the product of the primes P and Q, you know P and you know Q, you know P minus 1 and Q minus 1. And then the Euclidean algorithm gives you a number D that solves this equation. And then you can, then it's easy, the same argument. X to the E is congruent to C mod PQ if and only if X is C to the D mod PQ. So this is almost exactly the same as what we did in the previous case. If E is relatively prime to P minus 1, Q minus 1, you can compute D. And when you know D, you can find X. But the key thing here, which is so easy, it's easy to miss, is you must know P and Q in order to know P minus 1 and Q minus 1. If you are just given the modulus M, and even if you know M is a product of two primes, P and Q, it's too hard to find P and Q. That is, you have to factor M. Well, little kids factor numbers in elementary school when they're learning to multiply. But for big numbers M, there is simply no efficient algorithm to factor. So even if you know the modulus M is a product of two primes, you cannot find the two primes. If you know the two primes, you can solve this congruence. If you don't know the primes, you can't. You can't solve it. And that's exactly the situation which enables one to create a public key crypto system. So this is the RSA crypto system. So you can think of, here's Bob. Bob is like the CIA. And all over the world, you have spies for the CIA. And they get their information, and they want to send it back to Bob in headquarters. But of course, the enemy, or their enemies, always intercept these communications. So the messages they want to send back must be encrypted. So you need to encrypt your messages to send it to Bob. And you always want to keep changing your crypto system. So Bob wants to have a crypto system that he can send to all of his spies, and they can send messages back to him. But of course, he doesn't know how to contact these guys. These are, underground and deep cover somewhere. So Bob wants to publish to the whole world, make it available to everyone, an encryption method. So everyone knows how to encrypt their message to send it to Bob, and he wants to have a method that has this following nice property. Everyone knows how to encrypt a message, but only Bob knows how to decrypt it. So you have all these spies, like Alice is a spy out there. She needs to send her message to Bob. So here's what Bob does. Bob chooses two prime numbers, P and Q. He multiplies them. So he gets a number M, or capital N is the notation the book is using. N is P times Q. And also, Bob knows P and Q. Bob also chooses an integer E such that the GCD of E with P minus 1 and Q minus 1 is 1. So E is relatively prime to P minus 1 times Q minus 1. And Bob publishes to the world these two numbers, N and E. He doesn't say what P and Q are. He knows them, he doesn't tell anyone. That's his secret knowledge. But he multiplies them to get N, and he has this other number E, which is relatively prime to P minus 1, Q minus 1. And the encryption method is very simple. If X is the message you want to send, take X to the power E and reduce it mod N. And this for this C. So Alice takes her message X, that's the secret thing that she wants to send to Bob at CIA headquarters. Alice computes this integer C, just X to the E mod N, that's easy to do. Because everyone knows N and everyone knows E. They're announced to the world. And Alice sends C to Bob. That's all it is. So here's Alice. She sends to Bob this number. That's just her secret message, but what she sends is C, which is her message raised to the power E mod N. So this exponent E is sometimes called the encryption exponent, the encryption power. This is the encryption exponent. You encrypt by taking your message and raising it to the power E mod N. How does Bob decipher Alice's message C? Well, because Bob knows P and Q, remember N is P times Q, N knows these two factors. So Bob has calculated the number D, which is, that satisfies D times E congruent to 1 modulo P minus 1, Q minus 1. Bob knows this number D. D is the decryption exponent. So all Bob has to do is, how do you get x from c? C to the power d mod n is x to the e to the d, which is x to the d times e. dE is congruent to 1 mod p minus 1 q minus 1. So this is x. X is just congruent to c to the d mod n. So it's easy for Bob to decipher the message. He takes the secret coded message C that he got from Alice, raises it to the power D, and computes it mod n, and that's the number x. And who else can decipher the message C? Well, the outside person trying to find out what the secret is, Eve, she knows N and E, but she doesn't know P and Q. And Eve cannot compute a D that satisfies D times E congruent to 1 mod P minus 1 Q minus 1, unless she knows P minus 1 and Q minus 1. And she doesn't. The only way, well, the way to find these numbers is to factor capital N, but you can't do that. It's just too hard. And that is the RSA Cryptosystem. So let me do an example to show you how it works. And the text uses what it calls a small example. It's not that small, but let me just go through it. So this is an example. So Bob chooses 2 primes. P equal to 1223 and Q equal 1987. So N is P times Q. So if you multiply 1223 by 1987, well, it says in the book what the product is. You can also do it by hand, but I'm going to do it as I enjoy it in the chat. In Maple, I like Maple because I teach it when we teach calculus at Lehman. Any computer system and some calculators would also do this as well. Let's see. $12.23 times 1987. My calculator gives me exactly what the book got, which is 2,430,101. And I want a number E, which has the property. Oh, so that's P and Q. What are P minus 1 times Q minus 1? So P minus 1 is 1222, and Q minus 1 is 1986. And if I multiply them together, 1222 times 1986 I get 2,426,892. Yeah, that's good. The book and I get the same thing. And we want to find the number E, where the GCD of E and P minus 1, Q minus 1. That is the GCD of E and 2,426,892 is 1. And Bob chooses the number E equal to 948,047. And I just want to check. On my computer, if I take 948,047 and the GCD with 2,426,892, I do get 1. So this works. So Bob publishes, makes public the pair NE, where N is 2,430,101, and E is 948,047. So this is N, and this is E. And everyone knows them. Now, Alice wants to send a message to Bob. So Alice's plain text message, what she wants to transmit is the number 1,070,777. So this is a number which is between 1 and capital N, which is 2 million and something. But of course, Alice doesn't send her message, she needs to encrypt it. So the message she sends, she takes X to be equal to M to the encryption exponent E mod N. That means X is going to be congruent to 1,070,777 raised to the power 948,047, and then reduced modulo capital N 2,430,101. These look like big complicated numbers. Let's see whether Maple will solve that for me. Maple's pretty good. These look like big numbers, but of course, they're not really that big. So I want to find the Maple, use what is called the integer remainder function. If I take 1,070,777 raised to the power oops. It might be too big for my computer. I'm really surprised. Let's see. So the message I want to send is 1,070,777. And my encryption exponent is 948,047. And my modulus n is equal to the product of 1223 and 1987, which was this 2,430,101. And I want to know whether Maple can calculate n to the power e modulo n. Ah, it did. Oh, wow, it did. And I got exactly the same number the book got, which is very good. That is, this number x is in fact 1,473,513 when I compute this and reduce it modulo that. So the message that Paula sends to Bob, what Bob receives is x equal to 1,473,513. And what does Bob do? How does Bob decipher this message? Bob calculates x to the decryption exponent d mod n. So this is x. The decryption exponent is, well, so again, this is something one has to do. The computer will do this if you programmed or if it has programmed already, including algorithm. Remember, we have the encryption exponent e is 948,047, and we want to find d such that de is congruent to 1 modulo n. N is the product of our two primes. Sorry, de is congruent to 1 modulo p minus 1, q minus 1. And when you do the calculation, your decryption exponent is, you have to work with slightly large numbers, 1,051,235. So we have to see, we have x is 1,473,513, and we want to raise that to the power 1,051,235 and reduce it modulo n, which is 2,430,101. I'm going to do it on my computer and see what I get. So I have d, my decryption exponent is 1,051,235. And I want to calculate the integer remainder, at the least non-negative residue, of x of my ciphertext C. C was 1,473,513. So I want to calculate the ciphertext to the exponent e c, sorry, to the decryption exponent c to the power d reduced mod n. And when I do that, I get 1,070,077. So again, all of these numbers are worked out in the book, but it's nice if you have a computer to just to see how easy it is. So Alice had her secret message. She encrypts it, gets this number x, which is m to the e mod n. This is the number she sends to Bob. Bob raises this to the power d, and when he does, he finds n. And he can do this because he knows the decryption exponent d. And he gets d from knowing q minus 1 times q minus 1. But anyone trying to intercept and decipher the message can only do so if that person knows the p and q that are multiplied together to get n. And you can't factor a number in a reasonable amount of time. That is the Rsa Cryptosystem. And it's ultimately based on the fact that factoring a number factoring a positive integer into a product of primes is hard. Whew, okay, and now we've done enough to be able to do the homework problem. Awesome. That's it.